Hi again. We are still discussing integration by parts, but we will now consider a few exceptional cases, and today our main center of attraction will be repeated cases. Now, what I mean by repeated cases is the fact that integration by parts may not succeed when used the first time at solving an integral. Just a reminder of what the integration by parts formula does. Now, it is meant to replace an integral that is usually formed of a product of two functions. I've called them f and g prime, and replaces them by two new expressions, f times g, and a new integral that is formed of f prime times g, hopefully easier than the one we started off with. Reminder also of how we pick the function that we will call f. Now, if you encounter any inverse trig functions or logarithms, they would come first. Polynomials come in second when choosing the function that will play the role of f. And finally, trigonometric and exponential functions. Now, repeated integrals are usually the result of polynomials playing the role of f, as we'll see. Here's an example where we have x squared plus 2x, which is multiplying with cos. Polynomials come higher in our hierarchy list when it comes the time to choose it as f. Cosines and trig functions in general come in last. So x squared plus 2x will play the role of f, which means we will have to find for it the term that plays the role of f prime. That would be 2x plus 2. By default, cos of x will have to be g prime, and its antiderivative, g, is sine of x. So, placing all of these functions in the appropriate spots, our integration by parts formula will convert our initial problem into this new combination of terms, fg minus the integral of f prime g. I've highlighted in red the fact that our new integral is still formed of a polynomial with a trig function. The polynomial will still come first when it comes time to choose who will play the role of f. So the good news is the polynomial's degree has reduced compared to what it was initially. We started off with f as being x squared plus 2x, and now in this new integral, f is a first degree polynomial. However, we are still stuck having to do integration by parts. Considering f will play the role, will be 2x plus 2, then f prime is its derivative, 2. Considering g prime has to be sine of x, it's the only remaining term in the integral that is highlighted in red, then g, its antiderivative, is minus cos of x. So here's what we started off with. In black, you see the term x squared plus 2x times sine of x that we had already constructed from our first integration by parts step. And in red is the result of the choices we've made for the second integration by parts we have just started. I've put brackets because the signs will have to be distributed to the entire result of the integral that we are just constructing. There we go. I've distributed the minus sign in front of the brackets to all of the terms. Now, what used to be a second degree polynomial turned into a first degree polynomial after the first integration by parts. And what the second one has succeeded in doing is it has made 2x plus 2 become 2. So this is no longer a polynomial, but simply a constant. And luckily, this last integral is now one that falls into the basic integral category, and we can find its antiderivative directly. So minus 2 sine x. I've added a plus k for generality, as we always do. Now, in the case of repeated integrals, where a polynomial is the choice of f, and the exponential or the trig will play the role of g prime, there is a shortcut method, which I'll show you right now. So I'm going to construct a table where in the very first row I have written the choice we have made of the function that will play the role of f and the one that plays the role of g prime. You'll notice that in column f I've listed all the derivatives of f. So x squared plus 2x differentiated once becomes 2x plus 2, differentiated a second time becomes 2, and when we differentiate it a third time we get 0. At that point you can stop. As for g prime, which was cos of x initially, anti-differentiating it has made sine of x appear. Anti-differentiated again, minus cos of x. Anti-differentiated one last time becomes minus sine of x. We stop at the point where the derivatives of f become 0. On the left-hand column, I have alternating signs, pluses and minuses, always starting with a plus for the first row. And here is what we're going to do. We are going to consider the product of x squared plus 2x with sine of x. So there's kind of a delay between the f's and the g primes we're multiplying together. The signs on the left tell you whether you're adding these results or these products or whether you're subtracting them. So let's move on to the second term. Now we're going to subtract the product of 2x plus 2 with minus cos of x. And then we will add the product of 2 with minus sine of x. There's no need to go any further because at the next row we start having products involving zeros. And here we are. So our integration by parts has been split up into a bunch of terms, which are the results that we found in our table. And lastly, we can once again distribute the signs to make this a bit prettier. There you go. This result is the exact same result we obtained from our repeated integral process earlier. So I think we can call this a success.